Hi guys, welcome back. Today we're going to look at section 2.6, which is on the differentiation of implicit functions. So hopefully you watched the intro video with Dr. Taylor. He kind of explained implicit functions to you, what those were. So we're going to pick up today and kind of work some more problems and again talk about how this works. Okay, so big thing for today, just to remind you, is that these functions, these relations that we're going to solve today are not functions. You can't solve them for y. Okay? If you can't solve something for y, then that means it's not a function. It would fail the vertical line test when you tried to graph it. So they're still graphable. We can still work with them. We can still find points on them. We can find the slopes of those tangent lines to those points. But the difference is that it's not a function. And if it's not a function, then that's what we call implicit. Okay, these implicit relations, an implicit relationship between these variables. Okay, all right, so it tells you here that implicit differentiation, okay, is differentiation of a function where one variable, typically y, is not explicitly expressed as a function of another variable, typically x. Well, in layman's terms, pretty much is what I said, that you can't solve it for y. But the whole point of what we're doing today is to move on into section 2.7 when we don't have x's and y's. We're going to have a lot of different variables based on the application that we're working with, okay? For example, if we're doing a volume problem, usually with volume you have height and you have a radius. So then our variables would be h and r. There would be no x and y in that at all. So today we're going to begin with x and y just because those are the variables we've been working with. But keep in mind that this kind of a process will work for any function, no matter, or any problem, no matter what your variables are in it, okay? All right, so at the bottom of the first page, you have your steps. We'll go through the steps as we do them again. I do want to mention that when I do implicit differentiation, I use dy dx. It says here that you can find y prime or dy dx, okay? Because remember, that's all the same thing, right? So just kind of remember that, we've been writing f prime of x. That's the same thing as y prime, and, that German notation, Leibniz notation, dy dx, those all mean the same thing. So if you want to use y prime, that's fine, but I find that that's where students make more mistakes because you tend to not see this as easy because you're going to also have y's in your problem. And so if you lose one of those little prime marks, that y prime is going to become a y, and that's going to give you the wrong answer. I like dy dx because I can see them. I can't lose those. They're going to stay where they are. So everything I do, I'm going to do the dy dx, okay? All right, so it says when you're doing this, you're going to treat both x and y as a variable, as they should be, and you're going to take the derivative of each. However, when you take a derivative of the terms with x in it, you're going to do the derivative like we've been doing, and you're going to proceed as usual. When you take the derivative of any other term, and as we start, they're going to be y's, you're going to proceed and take the same derivative, but then you have to multiply the derivative by that variable in terms of dx. So we got to take the derivative of y with respect to x. Okay? All right. And then product, quotient, chain rules still apply. And then the whole point of this is once you finish taking the derivative, you're going to solve for dy dx. Okay? All right. So I know he explained this, but again, if you were to look at the derivative of 6x squared, okay, that is a term that has x in it, we would take the derivative, which would have been 12x, right? And we'd be done. That's what that says. However, if this was 6y squared, we would still take the derivative the way it is, 12y, but because it's not y, we have to take the derivative of y with respect to x, okay? We actually did that up here, we just don't write it. We're taking the derivative of x with respect to x. Well, if I wrote that, dx over dx, that's just 1, right? That cancels out, so we don't need it. So that's why everything we've done so far, we've just done the derivative. But it is the derivative of this variable with respect to x. Okay, so that's why we don't have to do it. Any other variable, when you take the derivative, you're taking the derivative of it with respect to x. So you have to have that for any other variable that you're doing. Okay, so that's the rule as we go through. All right. So Dr. Taylor did some examples with you. He did video problem 1 and 2. And then I want to mention to you, because I see this is still on the notes, I think when he did the intro video number 3, he just wrote down a 3 instead of the 3x. You know, he does these intro videos in a room by himself, so nobody was there to tell him that he wrote it down wrong. So I just want to mention that, you know, as if you went through it, hopefully you noticed that as well, okay? So just to be on the lookout. All right, so we're going to start with number 5. One of the big things, and I want you to understand, why is implicit differentiation so important? Why do we need it? You think about everything that we've done so far, they've been functions, right? So if you had, I'm just going to, you know, we've been doing cubics, whatever, you know, we've been doing any kind of graph. And if I gave you a point on the graph, there's only one point that has that x and y value. It's because this is a function, okay? So if you knew where x was, you could find y, and you could find the slope of the tangent line. Right? You could do all of that based on just x's, okay? Whatever x was, we could find everything else. Well, today, because it's not a function, if I look at this equation, x squared plus 2y squared minus 11 equals 0, that's an ellipse, okay? So if I look at the shape of it, it looks like that. Well, if that's the shape, that's not a function. So here's the problem. If I ask you to find the slope of the tangent line, let's say when x is 1, well, let's say here's 1. I've got a point here when x is 1, and I've also got a point here, right? So there's 2 ordered pairs that have an x value of 1. You know, whatever this is, y1, and then we have this y2 down here, right? We have 2 different ordered pairs. So if I ask you for the slope of the tangent line, which point are we talking about? Because the slope of this tangent line is a positive number. The slope of this tangent line is a negative number. So when I take the derivative, my derivative is going to have x's and y's in it because of this. I need to know both the x and the y coordinates so that I can find the slope of the tangent line. Versus this one, any function only has one point associated with each x, right? So there is no concern. I know if I give you x is, 3, you find that point and you know which point we're talking about. Okay, so again, if I give you x is 1 over here, I don't know which of the points. That's not enough information. So that's what implicit differentiation is doing. It's using x and y because we don't have functions anymore, which means there could be more than one point associated with some x value. All right, so look at number 5. We're going to start off kind of easy, kind of like Dr. Taylor's intro, and then we'll move into some harder problems. All right, so we're going to take the derivative. We're going to solve for dy dx. So remember, the rule is if you have a term with x in it, you take the derivative as normal and move on. So the derivative of x squared is just 2x. Okay, again, the derivative of x with respect to x, so I don't need to write that. Now, if you have a term with y in it, you take the derivative of that as normal, so that would be 4y. But because that's not x, we now have to multiply this derivative times the derivative of y with respect to x. So that's that dy dx. And again, you can use y prime here, but I don't like it as much because, again, students have a tendency to miss that. If you're used to doing that, then that's fine. All right, then we have the derivative of negative 11. That's a constant, which is 0, and the derivative of 0, which is 0. And you don't have to put the 0 in, but I'm just going through the steps. All right, so now we're supposed to solve for dy dx. So I'm just going to get rid of the 0 on the left. Okay, so I'm going to subtract the 2x over to the right. So I get 4y dy dx equals negative 2x. I'm going to divide both sides by 4y, and that'll be my answer. So negative 2x divided by 4y. You can leave it like that. It's not reduced, so we could reduce it. Negative 2 over 4 is 1/2, so we'd get negative x over 2y. That's the reduced form. But that's the derivative of y with respect to x. Okay? All right, now number 6, we're going to start moving on to a little bit harder stuff. So if we look at our terms, we have y squared times x. That's a product rule. Anytime you have the different variables, that's got to be a product rule. And then we have a quotient rule here, we're dividing. And then we have our regular x term and then a constant. Okay, so we have to do the derivative of y squared times x. That's where we're starting. All right, well, since that's a product rule, we start the product rule with the derivative of the first term. Well, the derivative of y squared is 2y, and since it's a y term, we have to tack on that dy dx. So that's the derivative of the first term times the second. We don't do anything with that. And then plus the first term, y squared. Now, because I didn't take the derivative of it, I only do dy dx when I'm doing the derivative. So this is a product rule where you just write down that term. So that I didn't do a derivative, so it's just going to stay y squared. Now times the derivative of the second. The derivative of x is 1. And because it's an x term, I'm done with that. Okay, so I'm going to put this in brackets just so you can see it, and I'm going to go through those steps again for you. So this is the product rule right here. So we started with the derivative of y squared, which was 2y dy dx, times the second term of x. Plus, then we do the first term, y squared, times the derivative of the second, which was 1. All right, now we're going to do the quotient rule, but I'm going to leave that minus sign out front, because otherwise we tend to lose it. So leave that minus sign, and now I'm going to do a quotient rule of just 5y over x plus 1. Okay, that's my quotient. So again, I'm going to put brackets. So the quotient rule is to take the derivative of the top times the bottom. So the derivative of the top is 5 dy dx, and then times the bottom of x plus 1. Okay, then minus the top function, which is 5y, times the derivative of the bottom, which is 1, all over the bottom squared. Okay, so there's the quotient rule for that. All right, now we're moving to the derivative of 3x, which is just plus 3, and then the derivative of 4, which is 0. Okay. So now we're going to clean up some of this stuff. So I'm going to go ahead and get rid of these parentheses. So I'm going to multiply. So that's 2xy dy dx. That's all one term. This would just be plus y squared. All right, again, I'm going to leave that minus sign out there for a minute, and I'm going to clean this up. All right, so what I'm going to do is I'm going to divide. I'm going to break this fraction up. So I'm going to take this term and divide it by that. And then I'm going to take this term and divide it by that. So I'm going to split it up into 2 fractions. So if I do this divided by this, I can cancel that with one of these, right? So that would give me 5 over x plus 1 dy dx. Okay, that's this term right here. I canceled this x plus 1 with one of those. All right, then I'm going to do minus. Now I'm going to just simplify this. So 5y times 1 is just 5y over the x plus 1 squared. Okay, plus 3 equals 0. All right, so I took this big fraction and I just broke it up into 2 separate fractions. Okay. All right, now I have to distribute this minus sign through now. So this is going to become the negative fraction. This will become positive, and then I've got to solve for dy dx. Okay, so I have 2xy dy dx plus y squared minus 5 over x plus 1 dy dx plus 5y over x plus 1 squared plus 3 equals 0. All right, so remember the rule. Any term that does not have a dy dx, so this one, and this one have to move over to the other side. Take the opposite sign. So leave the two dy dx terms over here. And we're going to move the others over. So negative y squared minus 5y over x plus 1 squared minus 3. All those go to the other side. Okay. All right, then we're going to factor out the dy dx. So that gives you 2xy minus 5 over x plus 1 equals all of this that's on the right. Okay. And then your last step will be to divide by what the other factor was, because you're trying to get dy dx by itself. So we're going to divide both sides by what's in the parentheses. So we end up with our final answer, negative y squared minus 5y over x plus 1 squared minus 3 divided by 2xy minus 5 over x plus 1. And that's fine to leave that like that. Remember, we don't have to simplify unless we're asked to. So there's the derivative. Now notice, this derivative has x's and y's in it. Right? So we need both x and y values in order to find the slope. And this is all this is. This is the derivative. So if I need the slope of the tangent line, this is what I have to use. Okay? Even number 5, the one above it, as simple as it was, I still need x and y to find the derivative because I need to know which point I'm talking about. Okay? All right, so hopefully that's making a little sense to you. All right, let's look at number 7. Okay, so on this one, they give you the relation that you're going to find the derivative of, and then they also give you the point. Okay, so now I know my x and y, so now I can continue and actually find the slope. So find y prime, okay, of this relation, and then we're going to evaluate it at 2, -1. Okay, so we're going to start with the first term, 2y. The derivative of 2y is 2. Since that's a y term, we have to take the derivative of y with respect to x. Plus 5, the derivative of 5 is 0, so I don't need that. Minus x squared, so the derivative of that would be minus 2x. And since it's an x term, I'm done. And then the derivative of negative y cubed would be negative 3y squared. And since that's a y term, dy dx, and always equal to that derivative of the constant over there, which would be 0. All right, so I only have one term that doesn't have dy dx, so I'm going to move it over to the other side. So I end up with 2 dy dx minus 3y squared dy dx equals 2x. And then I'm going to factor out the dy dx. So that gives me 2 minus 3y squared equals 2x. And then I'm going to divide both sides by that to solve for dy dx. So I get 2x over 2 minus 3y squared. So there's your derivative. And now we're going to evaluate it at the point 2, -1. Notice I need x and y. So x is 2, y is -1. So 2 times 2 over 2 minus 3 times -1 squared. And just watch your signs, watch your steps. So in the top you have 2 times 2, which is 4. In the bottom, I'm going to leave the 2 minus 3, and I'm just going to square -1, which is +1. So I end up with 4 over 2 minus 3, which is 4 over -1. So there's the slope of the tangent line at the point 2, -1. Okay? Now, this is a good example to show you why I don't use y prime. Now, if you want to use it, that's fine. But I'm going to write the same thing down, but instead of the dy dx, you can do y prime. Okay, so that's what it would look like. So I don't like doing this because a lot of times you guys either lose that prime sign or you do something silly like make that negative 3y cubed, right? You think that's a 1. And it seems simple, but there's so many little mistakes you can make when you just write the y prime because it looks too much like the regular y's. It's easy to lose the little prime symbol. So I just think you guys are in more trouble by doing that. Now, again, those of you that have done this and are okay with it and don't lose it, you know, that's fine. It's not that it's wrong. I mean, it's not wrong to do that. I just know that in my head, I'd rather see, I know which terms have the dy dx in them, and I don't lose those. It's easy to lose this over here, okay? But it's the same thing, so you can choose whichever one you want to do, but like I said, that's why I choose the dy dx, okay? All right, now these next two are kind of getting us ready for section 2.7. Because in section 2.7, we start applications of where this is in real life and are all over the place doing these implicit differentiation problems. But we need to be able to find a derivative with respect to any variable. Remember, I told you about the volume has radius and height, so there's no x or y in there. So look at number 8 and number 9. Okay, this is our basic area formula for a circle. No x's and y's in it. So the question is asking us to find the derivative of the area with respect to time. Notice that time is not even one of these variables. It doesn't have to be, okay? So what you have to be very conscientious of is what are you finding the derivative with respect to what variable, okay? What's in that denominator is hugely important, and it does not have to be one of the variables, okay? Look at number 9. We want to find the derivative of the volume with respect to time. Why are we keep using time? Because in our next section, you're going to see that that's how we have to solve the problem. We need the time that's involved. So the time usually isn't one of the variables, but that's what we have to find the derivative with respect to. Okay, so don't let that throw you. You just always take the variable that you're taking the derivative of with respect to whatever the variable is in the bottom. All right, so if we're doing a equals pi r squared, remember pi is a constant, a and r are your variables. So what is the derivative of a? That would be like the derivative of x, which would be 1, right? So the derivative of a, I'm going to write as 1, and then I have to take the derivative of that variable with respect to whatever it told me to. So in this case, it would be time. All right, and then on the right side, pi is a constant. And then I would take the derivative of r squared, which is 2r. And then I have to take the derivative of that variable, dr, with respect to time as well. Okay. So in this one, both my variables have to have that tacked onto it. Because I didn't have a t. The only variable that would be dt over dt would be a variable with t, and I didn't have that. But that does not mean you can't take a derivative. All right, so 1 times dA dt is just dA dt, and that's what it asked me to solve for. And then I'm just going to clean that up a little bit, so I end up with 2 pi r dr dt. So there's the derivative of a with respect to t. I solved for that. Okay. All right, so let's do it on number 9. A little bit harder because I got a product rule right here. So we want to find dV dt, and this is the volume formula for a cone, right? So remember cones look like that. So we have the radius, and then you have the height. So those are the variables in my problem. So again, no x's, no y's. Pi is a constant, 1/3 pi is a constant. All right, so take the derivative of the left side. The derivative of v is 1, and that's variable v with respect to t. Again, that's what it asked me to find. All right, so 1/3 pi is a constant, so I'm going to leave that out front, right? And then I've got r squared times h, so there's a product rule right here. So I'm going to do the product rule. So I'm going to start with the derivative of the first. So the derivative of r squared is 2r. Take the derivative of r with respect to t. Okay, that's the derivative of the first times the second, which is just h. That's the first half of the product rule. Now plus the first, r squared, times the derivative of the second. Well, the derivative of h is 1, and then you have h, the derivative of h with respect to t. Okay, so there's your product rule where you have 4 things, right? Here's the derivative of the first, that's the derivative of r squared, times the second, which was h, plus the first, r squared, times the derivative of h, which was 1 dh dt. 1/3 pi is the constant, it stays out front. All right, so clean that up. So 1 times dv dt is just dv dt, which is what I needed to solve for. All right, and then I can multiply 1/3 pi times all of this. So the only thing in the denominator is 3. So I have 2 r, h, and pi all in the top. So 2 pi r h over 3 dr dt. And you don't have to write, you can write those variables in any order you want to. You could write 2r h pi, it doesn't really matter. Okay, and then I'm going to do 1/3 pi times r squared. So that would be pi r squared over 3 dh dt. Okay, so if I were to multiply it through, that's what it would look like. Okay, so the whole point about this implicit, again, is that you understand what you're taking the derivative with respect to. So they will always tell you that, okay? All right. Let's try number 10. This is a WebWorks problem, and we always get a lot of questions about it, so I decided to put it on the notes so you guys would have this. All right, this looks very crazy, but it's actually not a bad problem at all once you think about how to simplify this. So it says if f of x plus x to the 7th times f of x cubed equals 11, and f of 2 equals 6, there's an ordered pair, right? That's the 0.26. Find the derivative of function f, at 2. Okay? All right, well, this looks kind of crazy to us, so we're not used to writing that. But remember, what is another way to write f of x? Okay, we know that f of x is the same thing as y. So instead of using f of x notation, change it to y. So this is the same thing as y plus x to the 7th, y to the 3rd equals 11. Now, doesn't that look much easier? We've already done these, okay? So it's, again, WebWorks problem. So they're just saying if you're paying attention to the notation, okay? So I replace this f of x with y and this f of x with y, and now I can take my derivative implicitly. So I'm going to start with the derivative of y, which is 1 dy dx, plus, and now I have to do a product rule, take the derivative of x to the 7th times y cubed. So start with the derivative of the first, which is 7x to the 6th, times the second, plus the first, x to the 7th, times the derivative of y cubed, which would be 3y squared dy dx. Remember, any term with a y in it, we got to tack that on. And then the derivative of 11 is 0. All right, now this is a great problem because this we tend to lose. So I have to leave that 1 there, okay? All right, so I'm going to leave the 1 and I'm going to clean up the rest of this stuff. So this would be 7x to the 6y cubed. And this would be 3x to the 7th y squared dy dx. Okay? All right, so I have to move anything without a dy dx over to the other side. So we're going to start with that. So I'm going to move the 7x to the 6th y to the 3rd over. So that leaves me my 2 dy dx terms. Negative 7x to the 6th y to the 3rd. Okay? All right, now, when you factor out the dy dx, this is why I like to leave the 1 there. There are 2 terms with the dy dx in it. If you guys lose that 1, some of you lose that whole term. So when you factor out the dy dx, you are left with 1 plus 3x, why wrote that so small? 3x to the 7th, y to the 2nd. Okay? 3x to the 7th. Sorry about that. All right, so I factored out the dy dx from both terms, so both of those coefficients out front have to be there. All right, so now we can divide. So we have negative 7x to the 6th y cubed over 1 plus 3x to the 7th y squared. All right, so that's the derivative. Okay, but I'm not quite done because it didn't just say find the derivative, it said find f prime of 2. Okay, so f prime of 2 means I'm plugging in 2 for x, but notice that there's also y's here, so that's why they gave you the ordered pair. So I'm going to use 0.26 to find f prime of 2, right? So I'm going to plug in 2 for x here and 6 for y. That's the derivative at 2. Okay, so again, all of these implicit problems need x and y to find the derivative, to find that slope. Okay, so we're going to plug in 2 for x, 6 for y, 2 for x, 6 for y. Okay. And then I would just do this on your calculator one at a time. So negative 7, 2 to the 6th times 6 to the 3rd will give you a negative 96,768. And in the bottom, if you do 1 plus 3 times 2 to the 7th times 6 to the 2nd, you end up with 13,825. Okay, and remember, WebWorks, just leave it as a fraction. That's your best bet. Obviously, this came from WebWorks. Look at that big number, right? That's how they work. Okay. So the big key about this was just that you understood that notation down at the beginning, the f of x. Just make sure you replace it with the y. Okay? All right. Last problem, number 11. Use implicit differentiation to find an equation for the tangent line to the curve 4x squared minus 4xy minus y cubed equals 84 at the point 1, negative 4. Okay, so we're finding the equation for the tangent line. So remember what that means. At the end, we're going to have to be using this y minus y1 equals m times x minus x1. So I need to know the ordered pair, xy, which I already have. What I don't have is the slope of the tangent line. So I got to find the derivative and then plug these numbers into that to find the slope. Okay? All right, so 4x squared. Derivative of that is just 8x. And since it's an x term, I'm done. Now, minus 4 times xy. This is a product rule, okay? So you can kind of do it any way you want to. I like to kind of leave, I mean, it just depends on how you want to do it. I like to leave the negative 4 out front and then just do the derivative of xy, right? That's the constant, negative 4. So now it makes it easier. I'm just going to do the derivative of x times y, a quick little product rule right there. So the derivative of x is 1 times the second, which is y, plus the first, which is x, times the derivative of y, which is 1 dy dx. Okay, so there's the product rule. Now we're going to do the derivative of negative y cubed, which would be minus 3y squared dy dx, another y term. And the derivative of 84 is 0. All right, so now I can distribute the negative 4 through both of these. Okay, so we've got 8x minus 4 times 1 times y would give you negative 4y, minus 4 times x times 1 would be 4x dy dx. And you've got the minus 3y squared dy dx equals 0. All right, so I'm going to bring these two over to the right. Those are my non-dy dx term. And because the 4y is negative, I'm going to write it first just so it looks a little nicer. Doesn't matter the order that you put them in. What does matter is the signs have to match up, right? So I'm going to take the 4y, make it positive, then bring the 8x over, make it negative. If you write negative 8x plus 4y, it's the same thing, okay? Doesn't matter. All right, now we're going to factor out the dy dx. So that leaves you negative 4x minus 3y squared. And then you're going to divide both sides by that. So we end up with our derivative. Dy dx is 4y minus 8x divided by negative 4x minus 3y squared. All right, so now we need to find the slope, okay? So we're going to plug in our x and y values, 1, negative 4. Okay, 1, negative 4. So we're going to remember y is negative 4, x is 1. So y is negative 4, x is 1. X is 1, y is negative 4. Okay? All right, so remember what this is going to give me. This is going to give me the slope, right? This is what the derivative is, m. Because remember, I have to have m and x1, y1 to write my equation of the line. All right, so 4 times negative 4, that's negative 16 minus 8 over negative 4. And over here we have negative 4 squared, which is positive 16 minus times negative 3. So that would be a negative 48. All right, so I end up with negative 24 divided by negative 52. That's a positive 6 over 13. So there's your slope. Okay, so now I have my slope. I have my point. Right, they gave me that in the problem. So now I can take these two guys and finish out my problem. Write the equation of the tangent line starting with that. So we're going to do y minus negative 4, which will be y plus 4, equals the slope 6/13 over x minus 1. So that gives you y plus 4 equals 6/13 x minus 6/13. Subtract 4 from both sides. If you subtract 4 with 13, that'd be 52 over 13 and 6. So we end up with 6/13 x minus 58/13. And again, use your calculators, right? You're going to do negative 6/13 minus 4. That'll give you that. Change it back to a fraction. Okay? All right. So that does it for the notes part of section 2.6. So I would go ahead and start doing some web work problems and get this practice in so that you don't forget how to work these, because it's a little different than the other sections, and you definitely need to know how to do this before we start section 2.7, okay? So keep working hard and let me know if you have any questions.